Hi everyone, my name is Karim Besbes, and today I will handle you to go through this study, heterogeneous modeling with common fluid properties and FMI terminals. And first, I will show you the motivation behind this study, the background is also to see some fundamental concept to understand more the topic that I want to present to you today. The challenges that we faced during the study and some technical core FMI terminals definition, ports and connector requirements, causality and interfaces. And at the end of the presentation, we'll see how we developed specific interfaces to a Simcenter Amesim library for the two-phase flow, which is TPF, and a new library, AmeTpfMedialibrary, where we can simulate and use the different fluid from a database. And at the end, to validate the concept and the methodology that we will present, we have a use case, a heterogeneous cooling system, where we will use the different technologies that I will present. So first, the motivations. So in Siemens, we have different customers using different tools and different modeling paradigms, causal modeling and acausal modeling. And with this study, we want to improve the integration of the Modelica world into the Simcenter Amesim platform using the causal system. So by combining causal and acausal modeling, we think that will help our customers to work in a better way and find the best approach for each domain. And also, and it's something very new for us, a way to use the physical properties of the fluid in both worlds with the same database. So some background. So you know normally, very well Modelica language. It's an acausal language that allow you to build systems in an acausal way. But in Simcenter Amesim, it's completely different. When you put a component or subsystem in the sketch, you need or you have to define the causality before connecting this submodel to another one. So the approach are very different when you model your system. And at the end, even if the result is the same, but the way that you create your system, it's completely different. How this Modelica world is already implemented in Simcenter Amesim platform. So we have an editor named Modelica Editor, where you can load the different MSL libraries. Right now, we are compatible with the 3.2.3 and 4.0.0 Modelica standard library. And between this Modelica editor, where you can load your different libraries or standard libraries, and as the platform Simcenter Amesim, we have the compiler developed by our partner Modelon. And thanks to this compiler, we can import the Modelica code or Modelica system to Amesim, thanks to the FMI generated by the compiler. At this moment, when we are in Amesim, we are causal because we generated the FMU, and then we can link the different signals to this FMU and the Amesim submodels, and then we can simulate. This is basic integration of the Modelica language in the platform. So now for the challenge to explain what we've done during the study, I selected a battery thermal management system to show you where we define the two systems, the causal systems and the acausal system. So here we have the full battery thermal management system, and we divided in two subsystems, a causal system from Amesim and a causal one from Modelica. And we replace the subsystems from Amesim by another subsystem, but in Modelica. So this was the first challenge: find the right models in the different resources in the Modelica website to switch the original components from AMSIM to another from Modelica. And then the second challenge was to find the right interface, or to develop the right interface between these Modelica components and the AMSIM components. And finally, ensure the compatibility, or ensure the continuity of the properties between Modelica and AMSIM. Okay, so for that, to create this hybrid or heterogeneous system, the first thing that we had to do is to implement the FMI terminals concept in this specification that we used at this moment, so FMI 2.0. On the right, you can see a scheme where you have Simcenter Amesim on the left and a Modelica system on the right. If you imagine a Modelica model that you want to connect to Amesim, you need to first see the connection and the variables you have on the connector of your Modelica system, and ensure a kind of consistency between this connector, Modelica connector, and the physical port defined already in Amesim. And for that, we need an interface. And to understand, or to let Simcenter Amesim understand that this connector from Modelica world is a terminal and can be transferred or translated into a physical port for Amesim, it needs to follow certain rules that we set terminal requirements. And one of the rules is writing an annotation, a tool vendor annotation, saying which type of port we have for this connector. And then we convert this connector into a physical port. And during the compilation, we see this XML file. Here it's only an example of this kind of translation, where we can see how the terminal concept has been used in this compilation to import the FMI. So now let's move on to the port and connector requirements. So thanks to the terminal, we can translate or transform a connector, Modelica connector, into a port, but we need to follow certain rules to generate this terminal successfully. The first rule is to have the same variable order of the order of variable we have in the physical port in Amesim. So in the left here, we have in fact the samples of connectors or of ports in Amesim world. So if we want to do, for example, the TPF connection or TPF ports, we need to be sure that we have the same order defined in the physical port in Amesim, the same causality for sure, and also the same type, the same unit. And at the end, in this connector, we need to define two things: a Modlon tool vendor annotation and a Simcenter tool vendor annotation. The Modlon one is very important. It allows the customer at the end, the user, to put only the interface on the top level of his system to avoid too many modifications on the original system that he needs to connect to Amesim, only the interface. And due to the fact that the connector is in the interface, it won't be on the top level of the system, and it creates an unbalanced system. To avoid that, and to take into account this connector as a top-level connector, we have this Modlon is top-level equal true annotation to minimize the effort of the user. When he put only the interface, he can connect it and generate into an FMU for Amesim. So how to build a Modelica interface now, thanks to the port and thanks to the FMI terminal. So a Modelica interface needs to be causal, or needs to translate a acausal connector to a causal connector for Amesim. And for that, this is the rule. So here it's an example on the left for a thermal interface for Amesim. So for thermal, we have two variables, heat port and temperature. So as you can see, we manage the consistency of the unit because it's not the same unit in Amesim and in Modelica. And we manage also the energy balance, considering the flow types or stream specificities. And now let's do it, but for the TPF. For our use case, the use case that I presented at the beginning of the presentation, getting a cooling system in the loop and trying to define the interface between them. So here it's a bit tricky because we have several things to manage. So as you can see here on the scheme, we have the unit, the variables inside the typical fluid connector in the Modelica world, so defined by pressure, flow, mass flow rate, and different streams. And on the right, we have the TPF connector following the same rules that the two-phase flow library is giving to us here. And then we create the interface. To create the interface, we need to manage the consistency of the causality, as I said, the unit consistency, and the mass and energy balance dealing with flow and stream. And this is the part that was a bit tricky because the concept of flow and concept of stream doesn't exist on the causal world, and especially in Simcenter Amesim. To manage that, in fact, we had to think about two use cases when the mass flow rate comes from Modelica and go to the Simcenter Amesim world. And for that, we use the in-stream function to be sure that the enthalpy that we send to Amesim is the one coming from Modelica, so the one coming inside the interface. And the second use case was to say, okay, now we have the mass flow rate coming from Amesim and go to the Modelica system. And at this moment, the enthalpy, or the enthalpy flow rate, is equal to mass flow rate multiplied by the enthalpy, depending to the pressure and the density, which is in this causal system, which is the entry to this interface. Now let's discuss about the AmeTpf library. One of the, for me, the most important work that we did for this integration ensures the continuity of the fluid properties between Modelica and Amesim. So we developed a full library for media properties. In this table, you can see all the fluids available in this library. And you can see here the architecture. So this architecture has an inheritance from the Modelica standard library. So it's completely standard. It's following the standard of the MSL. So each system is using the MSL for calculating thermodynamic properties. You can use this library directly for that. Behind the scene, there is an external object called in the same time by Amesim and by Modelica, and then we ensure the continuity like this. Here, a typical example of thermodynamic function that we have in this library, and when we can see the header called to use the right external object. Okay, so now we did a comparison just to be sure that our implementation is good, because we already validated the thermodynamic properties of fluid calculation through the years, the past 10 years maybe, or maybe more, in Simcenter Amesim directly. But here, this comparison and validation was only to be sure that our implementation in the Modelica system is okay, is good. So what we did, we calculate, or we do some example from different libraries. We take some example from different libraries, Steel Media, open source part libraries, MSL, and CoolProp. And we selected 3 refrigerants, and we draw the deviation across a temperature range of relative of a critical pressure, critical temperature, and we draw the pressure and specific enthalpy by evaluating the density. And we saw this deviation between AmeTpfMedia and the other library. So the first one on the right bottom, the left bottom, sorry, we can see CoolProp Steel Media MSL library results compared to AmeTpf. We can see that it's quite, the deviation is quite acceptable. For CoolProp and Steel Media, for the CO2, it's quite acceptable too. And for R134A, it's almost negligible for this one, between coolprop, MSL, and AmeTpfMedia. And for the performance, okay, so this part is kind of benchmark showing the performance of each library, StillMedia, coolprop, and AmeTpfMedia and MSL. But the point is not to say here which library is the best in terms of performance. It's only to say that we have a library, a new one, AmeTpfMedia, having a comparable performance against the different other well-known libraries calculating the properties, fluid properties. So for this benchmark, we use a thermocycle heat exchanger, and we calculate the water and CO2 and analyze the performance of this calculation for both fluid and for the three libraries, StillMedia, AmeTpfMedia, and coolprop. So you can see the performance in red. In red, we have AmeTpfMedia. In yellow, StillMedia, and in blue, coolprop. For the CO2, we have the same thing, the same color. So you can see StillMedia is better, a bit better, but it's, yeah, as I said, it's just, at least we can see that the performance is quite comparable to the other libraries. So now for the validation and for showing the results we get thanks to these different studies, we have this use case scenario where we have an evaporator from Simcenter Amesim, and the other components has been developed or has been used from the Modelica thermocycle library. So we separated the system by using the interfaces that we presented, and we add the new components from thermocycle. Here, the pre-design data that we use to design step by step all the equipment or all the systems that we bring from Modelica to have the same behavior than the original one, fully Simcenter Amesim one. And after that, we get these results. So here we have this view where we have the different results of the the behavior. Sorry, the behavior of the different important variables, like the cooling power, the pressure at the compressor, the specific enthalpies at the expulsion valve, and the mass flow rate in the system. And here we have the comparison between the homogeneous system, fully causal, fully from Simcenter Amesim, and the heterogeneous one created thanks to this AmeTpfMedia and the TPF interfaces. As you can see, we have quite similar results in the dynamics of the system, except for the expansion valve. And for the steady states, the results are very, very similar. Now let's move on to the conclusion of the presentation. So key achievements: seamless integration of Simcenter Amesim and Modelica components with these common fluid properties. And we validated this work through a cooling system case study. The technical contributions here: the robust physical interfaces between modeling environments, consistent fluid properties handling across Simcenter Amesim and Modelica, efficient causality management at boundaries. And for the industry, what are the benefits of this work is flexibility in component selection and modeling approach, leverage best features from both environments, and reduce development times through component reuse when we have a Modelica legacy, for instance, and enhanced modeling capabilities for complex systems. So current limitations, I didn't mention it, but we created only the TPF, the two-phase flow interface, in a air causality. For now, it's a limitation, but it's okay because this limitation, we can overpass this limitation by adding a new capacitive. I don't know if you, the causal approach needs to follow certain rules, and if you have a capacitive component, you need to follow it by a resistive component. So if we have a TPF interface R, or if we need a C TPF interface, we can overpass this by adding in the system, in the original system, a capacity to reverse the causality and then allow the connection with this TPF interface. And then last limitation, it's about internal communication. We saw that, for instance, if we need the mass between the mass during the initialization of a system, especially in a two-phase flow system, right now in the FME standard, there is no kind of possibility to connect the mass calculated in the system and the mass that we need in the Simcenter Amesim system. So it's something that we lack right now on the FME standard, a way to propagate some informations in allowing the initialization of the system, a better way to initialize the system. And now future work opportunities, enhanced communication protocols between environments and expanded fluid properties database, because in the two-phase flow library, we have also mixtures. We can define mixtures, and this is missing right now in the AmeTpfMedialibrary, but it will come a way to create mixtures in this library. Thank you.